All right, so we're going to look at electrostatics specifically. We're going to be looking at what is charge, how is charge carried from place to place, and how do we measure charge. So there are four fundamental forces in nature. We have gravity. We've studied that in depth. You're familiar with gravity. Electromagnetism, this is the force that we're working on now. Then there's a nuclear strong force and nuclear weak force. Every interaction that we see in the universe between any two objects can always be narrowed down to one of these four forces, or a combination of these four forces. In order for there to be a force of gravity, you have to have mass. In order for there to be an electric force, we have to have charge. So charge is to the electric force like mass is to the gravitational force. To have an electromagnetic force, you have to have charge. So as you know, there are two types of charge. We have positive and negative charge. Ben Franklin's the one that first coined these terms of positive and negative charge. If I have a positive and a negative, then they attract each other. But if I have two positives, they repel. Just like if I have two negatives, they repel. So we can sum it up in that way. Here's a table that shows the fundamental units. The first several ones are ones that we've used in the past. Distance, which is we use that in a formula as an x, and we use the standard SI unit, the meter, which we mark with just an m. Time is t. We measure the standard SI unit for that is seconds, and that's abbreviated with an s. Mass, m. For the unit, it's a kilogram, kg. Force, F, Newton. Charge, here's the new one. So these ones you're familiar with. The quantity of charge we mark in a formula with a Q. We measure it in units of coulombs, and that gets a capital C for the symbol. Structure of the atom. I'm sure you're all familiar with this structure. You got the nucleus in the center. Nucleus is made of protons, neutrons. You have electrons, which are, in a sense, orbiting the outside, zooming around the nucleus. The electrons have negative charge. The protons have positive charge. Well, if we look a little bit further into these, it's interesting to know about the structure of the subatomic particles. An electron is really a very small, very light object. The proton, on the other hand, is massive. It's huge. It's actually 1,800 times more massive than the electron. So it's kind of like an elephant compared to a mouse. The electron is very light, very small. Proton, massive. However, despite these differences in masses, differences in sizes, the charge of a proton is equal to the charge of an electron. Though they're opposite in charge, the electron is negative, the proton's positive, they have the same amount of charge. A single charge is called an elementary charge. So if I have one electron, then that's an elementary charge. And the reason for that is because I can't take an electron and split it in half and have half a charge. One electron is the smallest amount of charge I can have, just like one proton is the smallest amount of charge I can have. When we study quarks, you'll find out that we actually can break an elementary charge into pieces, but we're not going to worry about that for now. A couple of interesting facts. All electrons are identical. All protons are identical. It's not like I can identify one electron or separate one electron from another, or I have a single proton. I can't say, oh, there's Henry the proton, and then there's Fred the proton. No, all protons are indistinguishable from each other. All electrons are indistinguishable from each other. And yes, I'm at school, so you just heard an announcement. That's fine. An elementary charge value, remember I said before we measure charge in coulombs? If I were to take a single electron, it would have a charge value of 1.6 times 10 to the negative 19 coulombs. I'll provide extra credit to any student that wants to explain why there's so little charge in an electron or so little charge in a proton. But to restate that, an elementary charge value is 1.6 times 10 to the negative 19. So proton, a single proton is positive 1.6 times 10 to the negative 19 coulombs. A single electron is negative 1.6 times 10 to the negative 19 coulombs. And if we were to flip this on its head, take the inverse of that number, another way to say it, I would need this many protons, 6 times 10 to the 18 protons, to get 1 coulomb of charge. So that's a lot of protons. 6 with 18 zeros after it. Charge is quantized. Elementary charge is 1.6 times 10 to the negative 19 coulombs. So if I have 1 electron, then I have that much charge. If I have 2 electrons, I have 3.2 times 10 to the negative 19. You can never have an amount of charge in between those. It's always, another way of saying it, it's always going to be a factor of, the amount of charges will always be a factor of 1.6 times 10 to the negative 19. But again, that's a relatively small amount of charge, so it allows for a lot of different possibilities. Scale of the atom. Here I have an atom, let's see, this is 1, 2, 3, 4 protons. If I go to my periodic table, 5 protons means it's a boron atom. 5 protons. Hopefully I can get back to the PowerPoint. All right. So this is a boron atom with electrons zooming around. This is a typical picture you see of an atom. But the truth is, the scale that you typically see is not anywhere close to the truth. The nucleus is actually a little tiny speck compared to the size of an atom. The analogy I usually hear is if you have a football field, is the atom, then the nucleus is a nickel in the middle of the football field. But we usually picture it like this. Why do you think that's the case? Think about that. It's very similar to why do we never see an accurate scale model of our solar system. Same kind of thing is going on there. Charge is conserved. It's never created, never destroyed. It just moves from place to place. So if I charge up an object, I'm not creating charge. I must have put charge on there from somewhere else. Net charge, okay. Here's where we begin to look at some math. If an atom has an equal number of electrons and protons, then it has 0 net charge. Remember, a proton has the same amount of charge as an electron. So if we have even numbers of protons and electrons, then it's a 0 net charge. However, if I were to take an atom and give it some extra electrons, so here I have a helium atom, 2 protons, with 4 electrons orbiting, then that means it has a negative net charge. And in this case, we would have a charge number of -2 because of 2 extra electrons. Helium atom, 1 electron, so it has a net positive charge. So in this case, I'm missing electrons. And the charge number we would say as +1. Electrons, extra missing or equal. Well, first, I was hearing about 2 atoms are talking to each other. One atom says to the other atom, hey, I'm missing an electron. The other atom says, are you sure? The first atom replies, wait for it, I'm positive. Had to throw in a little bit of humor there. Physics humor, so good, I know. I'll wait a while for you to stop laughing. Okay. So charge number, as we pointed out before, is the difference between the number of protons and the number of electrons. So if a helium atom has 2 protons and 1 electron, it has a charge number +1. A uranium atom has 92 protons. If it happened to have 98 electrons, what would the charge number be? I'll give you a few seconds, or maybe pause the video, think through that. Hopefully you got the charge numbers -6. We'll do a few more. Oxygen atom has charge number of -2. If you go to your periodic table, oxygen has 8 protons. So if it has 8 protons and a charge number of -2, how many electrons and protons must it have? Well, 8 protons -2 means it has 2 extra electrons. Nitrogen atom charge number +5. Go to your periodic table. Nitrogen has an atomic number of 7. So that means it has 7 protons. How many electrons must it have? If you said 2, well done. Okay, amount of charge. Now we can actually start looking at the number of coulombs within various atoms. Helium atom, 2 protons, 1 electron. The amount of charge, it has a -1, or I'm sorry, +1 charge number, so it has 1.6 times 10 to the -19 coulombs. Basically, you take the charge number and just multiply the number of, or multiply it by the elementary charge. Uranium atom, 92 protons, 98 electrons. What's the amount of net charge on the uranium atom? We have -6. Multiply that by 1.6 times 10 to the -19. This should be negative 9.6 times 10 to the -19 coulombs. Helium atom, 2 protons, 1 electron. Amount of charge. This seems to be a repeat of the previous slide. All right. Here's where I show off my PowerPoint skills. Look at that amazing animation. The purpose of this is to talk about in a solid. The structure of a solid means that the atoms, the nucleus of the atoms, are locked in place. So the nucleus locked in place, the atoms locked in place. What is it that's carrying charge? If I put charge onto something, I'm not moving the nucleus. I'm not moving the protons around. It's always the electrons that are carrying the charge. So whenever I give something a negative charge, I'm giving it electrons. Whenever I give something a positive charge, I'm taking electrons away. So let's look at a few examples here. If an object has a net negative charge, it has extra electrons. If an object has a net positive charge, then is it got extra electrons, missing electrons, or an equal number? It's missing electrons. It's not that it has extra protons. It's that there are electrons that were removed from it. This is probably the most confusing part of the whole thing, is understanding an object with net positive charge isn't because it was given positive charge. It's because negative charge was taken out of it. But, of course, Ben Franklin, who's the one that first talked about this, had no idea about the structure of the atom. He had no way of knowing that we were taking electrons out. So we won't hold it against him. If an object has a net zero charge, then, of course, we have an equal number of electrons. What if an atom starts off with 20 protons, 20 electrons, and then becomes positively charged? Are the electrons extra, missing, or equal? What do you think? Hopefully you said must be missing electrons. All right. Here's some vocabulary words for you. Electrostatics, charged particles, coulomb, elementary charge. Having watched this video, you should know about these vocab words. You should be able to define them for me in class tomorrow. This will be due in class tomorrow. Draw a carbon atom, give it a neutral charge. You're going to have to get a periodic table and see how many protons, neutrons, and electrons a carbon atom would have. Then I want you to draw a second carbon atom. And this one will be missing 3 electrons. Then figure out what is the charge number of the situation number 2, and what is the amount of charge in situation number 2. Lastly, if you have a net charge of 5.6 times 10 to the -14 coulombs, how many electrons would you be missing? I'll give you a hint on that. It's going to be a lot more than 10. All right, so again, in class tomorrow, I want you to be handing in this sheet. It's going to have a picture of 2 different carbon atoms. Number 3 and 4, you're doing calculations. Number 5, you're doing calculations. Be ready to hand those in.